morning for everyone. Okay, today we are here for the third section of the CINE Conference 2021. It's my pleasure to be the chair. My name is Juarez Lopes Ferreira da Silva. I am one of the PIs from the Center for Innovation in New Energy, and also the coordinator of education and knowledge dissemination for CINE. And then I also have a faculty member here in the São Carlos Institute of Chemistry, University of São Paulo. It is my pleasure to be the chair today, here together with the very special today speakers, few of them that I have learned a lot with them. And then before we move to I give the word and the floor for them, I just like to give some few remarks. First one, today afternoon, we're going to have our additional section in the afternoon. We have several additional talks, 6 talks, very impressive talks, as I could see now in the test of the slides. And then I want to motivate everyone to put your questions on the questions and answers. Then this will make my life easier a lot. And then you also help to the discussion, okay? And this is, I think, is a very welcome. I talked with our director, she's our first speaker, and she even thinks to give a prize for those the most hard question that she received, or all the speakers, we are thinking to give a prize for the future, okay? And then the prize will be decided later, of course.
Don't be shy, don't be shy, ask questions.
Okay, that's very important for us, okay? And then I would like to say, for example, this conference have been, to say, a very successful conference up to now, okay? It's an online one, and the next year we expect to have it as a presential one. Ana Flavia, our director, Ana Flavia, have already provided a date in October, and then we are committed to make it to happen, and then we expect that to be a great pleasure next year too. However, we are doing online, and I have learned and then a lot in the last 2 years, nearly 2 years, work online, that the online conferences, online lectures, meetings and talks works very well, okay? And then this is really important. Our world is moving on a direction in with the digital transformation, when you combine the expertise that we have learned using new tools that was developed in very fast approach. For example, before of the COVID pandemics, I was often a user for Zoom, and today is our basic tool, okay? And then we are here today, use that, it helps a lot, and also to provide the possibility to have very special guests for our conferences. For example, today we're going to have Flavia Ribeiro from the Purdue University, one of the, to say, partners from CINE with the C2C agreement that was signed based on the effort that was conducted by Fábio Coral Fonseca, and then it's provided a possibility for him to stay with us today and to deliver his talk. And also Professor Prahant Kamat, that is really also important, and there's a possibility that provides us in the end does not take their very long time for them to take part, because a travel from that from United States or to Brazil take 12 hours and so more. And then the present situation, I think, is very important, and it's very helpful that the digital transformations make our works better, and you contribute for the future. Okay, with that, I just close it. And now we're going to move for the first speaker. Our first speaker is Professor Dr. Ana Flavia Nogueira. She is from UNICAMP, the Institute of Chemistry. Is a person that I have learned a lot in the last 2 years, because since before CINE we do not know each other, but now today we are very good friends and working together to make CINE successful. And then, Ana Flavia, now the floor belongs to you. I am very happy to be the chair of the conference of your section. Okay, now the stage with you.
Okay, thank you, Juarez, for this kind introduction. So today I speak about in situ and operando experiments using conventional and synchrotron radiation, from electrochemistry to perovskite solar cells. Okay, so first I have some special thanks to my team at UNICAMP, that collaborate in this presentation, Professor Pablo Fernandes, Professor Cláudia Longo, and Professor Juliano Bonassin, and also to the team at the Synchrotron Lab that is located in the Centro Nacional de Pesquisa em Energia e Materiais. So in CINE, we have the now the SIRIUS, that's the new, is the 4th generation synchrotron lab, but all the experiments that I'm going to show here today were performed in the old machine, the UV-vis, that was turned off in August 2019. So by special thanks to Elio and Raul, and also to our sponsors, FAPESP and Shell. Okay, so what's DEC, our program, Dense Energy Carriers, is involved, is not only in the production of, for instance, green hydrogen or CO2 photoreduction, but also we are looking at development of emerging photovoltaics. But the core of our program is actually the in situ and operando experiments with the help of Professor Pablo, Professor Nagal, Arnaldo, and René. We are doing a lot of these in situ experiments. I'm going just to give you some glimpses today, which are very important, that actually link all of the projects at the DEC program. You're going to see that these in situ experiments are really important for us to understand the mechanism of reactions. For instance, you can understand more about the film formation in case of the solar cells. And I hope that at the end of my talk, I convince you that it's really important to combine and to have these in situ experiments in our day by day. Okay, the outline of my talk. So I divide in two parts. So the first part, I'm going to talk about some in situ experiments in metal halides, perovskite materials, and synchrotron light. And some few slides at the end of my talk about in situ and operando experiments in photoelectrochemical systems. So, okay, let's go for the first part of the talk. For those that know my talks, I always present this slide from Shell Sky scenario. So Shell is actually predicting if the future is renewable, and the answer is yes. And if you look at the scenario in 2020, you can see here that most part of our energy, about 32% is going to come from the sun, followed by wind and also the nuclear. So in order to have this 32% of energy from the sun, of course, there is a really challenge here. We need to do a kind of revolution in terms of in order to sustain this 32% of energy. And if you look at today, so why it's a challenge? Because if you look at today, 90% of the market of the photovoltaics is actually silicon. And what's the problem with the silicon? The processing is really very expensive, it's energy consuming. So in order to get this 32%, it's really important to develop new technologies. So really need to think about tomorrow. And for that, it means that I think we're going to need all of the technologies. But I also would like to point out the importance of the emerging PV for this challenge. If you could look here at these NRL charts, you have here the first and the second generation of photovoltaics. And you can see here down the bottom, the emerging photovoltaics, in the case perovskite solar cells. So you can see that the perovskite solar cells have recently achieved efficiency of 25.5%. This is above of silicon polycrystalline, and we are just 1% below the silicon, the monocrystal. So it's a huge increase in efficiency for this technology in very short period of time. So that's the reason that we really need to invest on this technology. Let me tell you more about this special type of perovskite, because perovskite is a chemical, is a structure, many oxides have these perovskite structures, but this kind of perovskite for solar applications or even light emitting applications is very special. You can see here that on the A side of this cubic perovskite, you see here that you can have organic and inorganic cations, and this makes a lot of difference The composition of these perovskites for solar cells are really, really special. You can also look here, you can see that for the B side, we have a cation that in most of the cases are lead, and X can be halide, bromide, or iodide. So these perovskites have many interesting properties, just to cite some of them. For instance, a very high absorption coefficient. You can tune the band gap because you can play with the composition, and most of defects are shallow. Just exemplify when you change, for instance, in this case, when you change the ratio between, for instance, the halides here, you can achieve like a very broad range in terms of absorption here from UV to almost to infrared. So this is very interesting. There's something you can do, also playing with the A side, with the cations as well, with the monocations as well. In terms of absorption, we are doing very well because it's a direct band gap semiconductor. You can see here that absorption is much higher even than gallium arsenide if you compare with silicon. In terms of defects, these materials are very defect tolerant. Why? Because if you compare, for instance, with gallium arsenide or gallium telluride, you can see that the threads are really in the mid gap. While for this metal halide perovskite, you can see that we have shallow threads, means that the threads are very close to the conduction band or to the valence band. So these are one of the some of the special properties of this semiconductor. And also in a lab, we can prepare this metal halide perovskite in many dimensions. For instance, this is this 3D bulk MAP. MAP is this, the well-known perovskite with the cation is a methylammonium cation. You can see this is the film for a 3D, but also you can prepare as a quantum dots of this perovskite. You can have like molecular perovskites or even what we call like 2D perovskites, not only in a kind of micro size domain, but also you can have like we call like, for instance, in this case, nanoplates, 2D materials. So what's interesting here is like from these quantum dots, even for these 2D materials, 2D perovskites, they have been used a lot in light emission applications. So in order to understand more about these perovskites, we can combine for instance, in situ and operando experiments, not only with the synchrotron light, but also you're going to see with like very common light sources that you can find in our lab. But talking about the synchrotron light can go from X-rays even to infrared. In terms to apply these techniques in the perovskite materials, these techniques allow us to, for instance, we can track the formation of this perovskite in solution. We can track the formation of this perovskite film, and even see what's going on during, for instance, for the crystallization step. This is really important for the perovskites. And also we can follow the initial steps of the degradation. I'm going to show you only 2 examples here because of the time. So starting with tracking the formation of these perovskites in solution. This is the synthesis of a 2D perovskite, where this the cation is a lone cation, which is a butyl ammonium cation, and this is our organic cation. This is a very simple reaction that we develop in our lab, that you can make this very nice film at the room temperature. I think I can play here the video, you can see. You can just mix these 2 solutions, at 2 solution of precursors, you can have this 2D material. It's a really fast reaction. These films are really bright, have a very, very interesting for light emitting applications. Okay, so the question here was, okay, can I perform this? Can I have more information about the, can I have more about the mechanism of formation of this 2D perovskites? Yes, we can even perform this reaction inside of the beamline. This was done, you can see here, this is our reaction. Of course, you can control everything from outside, including the injection of the solutions. And this was done in the SAXS beamline in collaboration with Professor Mike Tony, that is now in, it was done in Slack, but now Mike is in Boulder. So as you can see here, this is the data that you can get from the SAXS, is a 2D image. Of course, you have to treat this in order to get the 1D data here, where we have intensity as a function of the Q. Q is related to theta. Okay, so it means that you can follow. That's something interesting from these in situ experiments when you go to the synchrotron, because you cannot do it in your lab. You have to go to the synchrotron because we have this fast this detector here that allow us to view very, very fast acquisition of the data. So we can see here when you plot with time, you see the growth of this very nice peak here about 0.33. This is from the 0 to 0 diffraction peak. This from the stacking of these perovskite layers here. But also, as I mentioned, because we're doing this with time, we can also do some kinetics to look at our data and do some kinetics. For instance, you can look how about how the full width at half maximum vary with time. We can do some calculations here, and even you can to calculate the growth rate of these materials. For instance, we know that just right after injection, we have the solution of the precursors. Within the 10 seconds, we have the formation of the like individual slabs. In this case, for these perovskites here, we have the slabs are formed by 2 layers of octahedra. So N is equal to 2 here. And after that, you have the self-assembly of these slabs in a very 2D, very nice structures. We can even calculate, we know that 2 slabs takes about 6 seconds in order to self-assemble here. This work was the front cover and of chemistry materials in 2019. But okay, let's now go to the 3D, to the perovskite film that we use for solar cells. We can even compare, for instance, 2 different methods of preparation, the anti-solvent and also we are going to see here and the spin coating method. So prepare perovskite films are very easy. It's A plus B equal to C. You just mix 2 precursor solutions, as I showed you before. But you can do it in 2 different ways. For example, it's the same we are doing now in our lab. The most I'm going to show here, the first most used method to prepare the perovskite is the anti-solvent. I'm going to play this video here so that you can see. Okay, you spread the solution of your the precursor solution in a spin coater. Just before the end of the spin coating, you are going to drop the anti-solvent. And I want you to pay attention here that as soon as you drop this anti-solvent, you are going to see a change in the film and the film color, and where you see the formation actually of the perovskites. In this method here on the right, it's much more scalable. Here also you have the precursor solution here, but it is called like a blade coating process. You are spreading your film, and instead of dropping this anti-solvent, you have this flux of nitrogen here on the head of the knife that is actually crystallizing the perovskites. So as you can see here, the method on the right excludes toxic solvent. You do not pollute your glove box, for instance, because you do not saturate the atmosphere of your glove box. So it also allows us to go for instance, for large air. But in both cases, of course, you can have really nice perovskite film being formed. So what we did was we just before talking about the data that we got in the synchrotron, it's important to mention here that in all that process, what you want is the cubic perovskite, because this one here is the one that is actually photoactive. But it's quite impossible to get rid of the hexagonal phases. Those hexagonal phases, as you can see here, they are non-active for photovoltaics, because you can see that the octahedras are not linked in a 3D dimension. So we don't want this hexagonal phase, but it's really important to study them, because we are going to see that before forming the cubic perovskites, we pass through these hexagonal phases. So then we decided to go to the synchrotron again. see if you could see actually those structures, those hexagonal phases on a perovskite film. Yes, this is not, we did not operate this infrared nanospectroscopy in situ mode. Okay, but if the technique is going to be available, we hope soon again, because it was turned off in August, but it's going to be available soon, I think in January next year. So you can couple the synchrotron infrared with the AFM. I'm not going to details here, but it was possible for us to actually to map the composition of the perovskite, and you can see here all of these greener grains here on perovskites is actually, we assigned to this the presence of these yellow phases. So these yellow phases are there, and how important they are in the formation of the cubic perovskite. So this, then we went back to the synchrotron, now operating the GWOX in situ mode. So it was very interesting experiment, because we brought the spin coater from our lab. We set the spin coater on the beamline, where we could control outside the time to inject the solvent, or the time to actually inject even to turn on the nitrogen flux. So this is the spin coater. The X-ray beams come from this side. You have our detector, and the sample is here. So this is the data that you can get from this. This is 2D image, and then you can also plot your data in this form here, like Q as a function of the time. Remember that Q is related to theta. As you can see here in this data, as soon as you drop the anti-solvent, you start to see the formation of this very strong peak at Q equal to 10. And also the formation of other peaks that also is going to disappear with time. So we assign this strong peak here to 10 nanometers -1 to the cubic perovskite. This is the phase that really want. And also those peaks here, we assign to these 2H and also 4H hexagonal phases. So what's interesting, as we're doing this as a function of the time, you can plot the intensity of these peaks with time. And you see here clearly that first we are forming these hexagonal phases, and then these hexagonal phases are actually converted to the perovskite. So what happens now when you compare this with the gas quenching, when you use the nitrogen flux? This is the data that I showed you before here on the left. This is the new data on the right. You see here that in both cases, we are forming the cubic perovskite. Also, we are forming the hexagonal phases. But when you compare both of them, you can see here when you have this gas quenching, even after the end of the process of deposition, you still have the two phases coexisting. It means that, again, you have the formation of the hexagonal phases, then they are converted into perovskite, but the crystallization is much lower when you compare. So this allows us to have like a film with larger crystals. And in fact, in our lab, our records in terms of efficiency, it is about 21–22% is actually using this nitrogen flux instead of this anti-solvent method. Okay, so let's move to the second part of my talk, where we're going to show also the importance of this in situ in operando experiments in the photoelectrochemical systems. Of course, I'm not going to detail all of these two papers that I'm going to present, because first I don't have time, but I really want to show that these techniques are actually available here in Campinas. What's interesting from when you have a photoelectrochemical system, or there is a solid liquid interface, is that this in situ and operando experiments can track many changes in terms of activity of material. You can probe the reaction mechanisms. If you can look at the size of the solution, you can look at the solution side and sometimes to predict, for instance, the selectivity. So these are the techniques that are available here at the Chemistry Institute in Campinas. Most of them, I think all of these techniques are available in the group of Professor Pablo, René, and Nagal. You can see here we can have ultrafast, in situ ultrafast spectroscopy, X-ray absorption spectroscopy, and also Raman and infrared. And also here also we have this in situ differential electrochemistry mass spectroscopy. So in order to test our samples, our electrodes, or our solutions, Professor Pablo team developed this spectroelectrochemical cell that I think I showed you before yesterday. It's a really versatile photoelectrochemical cell that you can take everywhere. You can go to the synchrotron with the cell, or even you can work in a lab. So today I'm going to present this some data on the infrared in situ applied to photoelectrochemistry. And then you can say, okay, but this is very common. Of course, it's very common to have in situ infrared coupled to electrochemistry, but not to photoelectrochemistry. It means that we are also, together with in situ infrared, we are also shining, as you can see here on the bottom, we are also shining, we couple a solar simulator. So it means that you can get this in situ infrared in the dark, and also under, for instance, one sun conditions. I think this is the novelty of this technique that we developed here in Campinas. So I'm going to show two examples. One of them, it was this work here when we grew hematite nanorods, and we used as a co-catalyst this cobalt Prussian blue. It was a collaboration between my group and the group of Professor Pablo and Professor Juliano. If you know about the cobalt Prussian blue, you know that there are many oxidized states. You can have like cobalt 2 and 3, iron 2 and 3. So it's a really complex. What we observed, it was a real increase in the photocurrent when you have this co-catalyst. This was done in neutral pH, but this is an advantage. You can see here on this image the growth of this co-catalyst on the nanorods. But then it's really such a mixture of different oxidation states that it was only possible to understand the mechanism using this technique. Of course, I'm not to have time to go into details, but I just want to show you what?
1 minute.
1 minute, okay. I'm finishing. I'm just going to show here the difference. Here is the evolution of the infrared when you apply a voltage. You can see here the appearance of some bands, but when you compare the dark and with the light, you can see here that it's really different. And then with that, we propose the mechanism for oxygen evolution here using this material. And another example was Professor Claudia Long mentioned yesterday. It was in looking at the photoreduction of the CO2. They developed this copper oxide photocathode and apply a kind of overlay of this aminopolysiloxane on the top of this photoanode. It was a huge improvement in the photoreduction of the CO2. And in order to understand more about what's going on, also this technique was really important. We know that the CO2 is going, of course, to react with the amine groups from this aminopolysiloxane. You can see here, forming what you call like the chemical bonds here from this carbamate group, but only using this in situ coupled to a solar simulator that was able to see here the evolutions of these bands here that actually was assigned to the carbonate. We can prove that it was really effective in improving the reduction of the CO2. Okay, with that, I think I finished here, showing that in terms of the perovskite materials, they have extraordinary properties, but are very complex, sometimes unstable. I didn't have time to talk about the degradation. We did some in situ experiments in the synchrotron, also probing the degradation. But I think there are many open questions, what makes this field very interesting. In terms of, I hope that I convince you that the in situ experiments coupled to synchrotron radiation is really helpful in try to understand these problems. We have developed here in our program some different setups to perform these in situ techniques, and please just contact us. So the facilities are really open to our community. And you also don't need to go to the synchrotron, but you can see here, I think it was really important to show you that you can use in conventional techniques, for instance, infrared Raman, that are the cheaper. sometimes is more available that you can use in order to get more information about your system. So this is my, I think with that, I think that yes, there is a lot of things to be done. And I finish here. Thank you for listening to me.
Thank you, Flavia. Congratulate you. I know that we just beyond 5 minutes. And then, but when you start to talk about perovskites, it's almost impossible to stop you. Okay, I understand. You like so much perovskite, but now we have to move on. One of the first questions here is concerned about the, as far as the Flavia, the first talk, is concerned the perovskites. Is how are stable those devices for a long time run compared to silicon? This question is from Albert Petergood.
It's definitely a difficult question because if you listen to the companies that are planning to deploy this technology in the market soon, we have already one company from Poland that is already commercializing this technology. If you listen to them, they're going to say that they are very stable. And some of these companies are planning even to place these perovskite solar cells on the top of the silicon solar cells, so then you can have like we call like a tandem. Of course, in order to that, the two technologies needs to have the same lifespan. So if you listen to them, they're going to say, okay, it's are very stable, but I don't think this also convince the researchers. It relates to an open question. What you have to do is like you need to wait to see those solar panels actually working on the roof of like on the rooftop of buildings, whatever we're going to place them, and to actually to check if they're stable or not. In our community, is a huge doubt, concern about the stability of this this technology, but unfortunately I don't have the definite answer.
Thanks, Anna. Okay, and now I have a question for Ana Flavia. Ana Flavia, for example, suppose that I have my $20 million now, and then you say when you talk that 9% of the full cell in the world is silicon at the moment. But you also predicted for the sky scenario that in 2050, you'll be 32%. Okay, you have a very small now. And silicon is responsible for 90%. Suppose I now have $20 million, I want to put in the stock market to buy stocks from the company that has a technology that will be compete with silicon in future. You have perovskite, you have CIGS, cadmium telluride, you have several technologies. From your view, work on this field, what technology you compete with silicon really in future, in 10 years, 20 years?
Juarez, I don't think that actually we need to compete with silicon. We don't have to. And in my opinion, I predict that in the near future, and we're going to have all of these technologies working together. We cannot just pick one and just choose one. Of course, I think there are many opportunities here with not only with perovskite, but other emerging photovoltaics. And I think we have to, of course, if you tell me you're willing to invest, what's the advantage to invest in perovskites now? Because it's a new technology. It's a new technology. You see that the efficiency can go even higher than silicon, okay? But I think that we don't need to compete because we're going to need all of these PV technologies in the future. Okay. The problem with the silicon and the thin film is that actually you can, if you remember that charts that I showed you before, you see that in terms of efficiency, they're not growing much because they are reaching the theoretical limits. So we have chance here to grow even higher with the emerging photovoltaics. But at the end, we're going to need all of them.
See, thanks for the comment. What I mean by competing is the following fact. Silicon controls 9% of the market. Means the market is a business based on the efficiency and cost. Means what I mean is that point that I think is very important to see what to say. What technology you have a lower cost and efficiency that could compete to take some share, a larger share on the market, that will be important.
So if I have to bet one, in this case, if I have to pick one, this definitely is going to be the perovskite, because the other emerging photovoltaics, because my background is on dye cells, my background is on OPV. So I remember that it was really hard for me to achieve efficiency in my lab that it was like over 10%. This was never happened. It's only happened with perovskite. So the advantage of the perovskite solar cells is actually we can prepare them at lower cost, like some predictions say about like 1/3 of the price of silicon, and even that can be competitive because of the efficiency. I think this advantage, even if you compare with the OPV or even dye cells or the quantum dot solar cell. I'm sure that Professor Kamat, I don't know, I think, would you like to comment, Kamat? Please go ahead.
Kamat, if I want to comment, I can open the microphone for you. Your microphone is closed, Kamat. Yeah.
Okay. No, I think you covered every point in the sense that in the market, to get rid of a technology that already exists with a new technology has to be extremely transformative. If it is an incremental, the industries have invested so much money in the infrastructure and marketing. They don't want to do something new all of a sudden just because another one. Same way with the consumer, you come up with a product that is very good, like silicon lasts for 20 years versus a new maybe perovskite solar cell, same efficiency, same cost, but not tested for long term. The consumer is going to go for silicon. So unless you say, well, this one is 10 times cheaper and 5 times better, then it is transformative. I'll just give an example. We used to use floppy disk for computer. When floppy disk came, these memory sticks, we used to put it in. CD-ROMs came in. So they wiped out floppy disk. When CD-ROMs were the great for just short time, then the memory stick came, the CD-ROMs gone. So they were transformative. So same way in the phones, it's transformative. So in order to replace a well-established product, we need a transformative. LEDs were transformative compared to the tungsten lamp. And they became very cheap as they start producing. Look at lead acid batteries. We have not gotten rid of it, right? There is a big scope for that, but we don't have a product that it's 150-year-old. So at one end, we are all wishfully thinking that some new technology will take over with low carbon footprint. That is the only advantage of these perovskite is the low carbon footprint. And the silicon, one of the things they are doing is they are previously to slice it. So they grow these long crystals and then they slice these wafers. And the cutting blade makes a powder because when you thin a slice, so that is becoming thinner and thinner so that the waste is becoming less. And so that is one of the advantages. That's how they're reducing the prices and other things. So there are a lot of other ways to look into the ways. But I think what will happen is the perovskite, maybe in the tandem solar cell, will boost the efficiency about 30%. So that may be a way for perovskites to get into the game. Rather than competing, they need to join the race. That's my feeling.
Thanks for the comment, Kamat. Very insightful.
If you just allow me to do just a comment, last question, that's quite interesting.
Yeah, okay, I agree with you.
Yeah, the investors, they are going to want to have a certification, as Professor Kamat say, how much for the carbon footprint, how much water footprint, how much I spend of energy to go to the new technology. When you go to the new technologies, more people are paying attention, more things that were not used to pay in the past. That's quite interesting question. Thank you for Professor Kamat too.